Okay, 7.4 is on distribution by partial fractions. Okay, so there's this technique called partial fraction decomposition. And we're going to utilize uh, that process in order to do some integration, okay, to break up some integrals. So let's just jump into an example. If I have the integral of x squared plus 2x plus 1, or sorry, minus 1, all over 2x cubed plus 3x squared minus 2x. Okay, what I'm going to do is I'm going to factor the denominator here. And I'm going to get x squared plus 2x minus 1 all over. Pull out an x. I get 2x squared plus 3x minus 2 dx. Let's factor that guy. X squared plus 2x minus 1 all over x times 2x minus 1 times x plus 2. 2x squared can only come from a 2x times x. And the 3x comes from the 4x minus 1x. 4x minus 1x gives me the 3x. And the minus 2 comes from the negative 1 and the negative 2. Okay. We have that guy factored. Okay, dx. Now, what I'm going to do is I'm going to use partial fraction decomposition to help me break this up into 3 separate integrals. So what is partial fraction decomposition? Well, if I have linear factors like this here, x, 2x minus 1, and x plus 2, these are all x to the first power, I can rewrite or decompose this fraction into fractions that involve just each factor. So a over x, b over 2x minus 1 plus c over x plus 2. Okay, so we just do a, b, c if they're linear factors. We'll talk later what happens when we get stuff other than linear factors, but we're just going to start off with linear factors right now. And so we can say that this fraction on the left can equal something over x plus something over 2x minus 1 plus something over x plus 2. We can break it apart like that. Okay. Now I have to figure out, okay, well, what are a, b, and c? Okay. And what I can do to simplify for a, b, and c is I can multiply everything through by the lowest common denominator, which is x times 2x minus 1 times x plus 2, and we're going to multiply both sides by that common denominator, x times 2x minus 1 times x plus 2. We're going to get x squared plus 2x minus 1 on the left. And if I distribute this, okay, to each of those terms, one of the factors will cancel out in each of the terms. A goes to a times 2x minus 1 times x plus 2. The x term will cancel out with the x in the bottom. I'm sorry, I should say factor. The x factor on that I'm distributing will cancel with the x on the bottom in the denominator, and I'll just be left with these two factors, 2x minus 1 and x plus 2. For b, x will survive, but 2x minus 1 will not. And so we're just left with x times bx times x plus 2. And then for c, an x will survive and a 2x minus 1 will survive, and the x plus 2 will not. It will cancel out. Okay, now with all linear factors, we can use something called the Heaviside technique. Okay, named after Oliver Heaviside, who's a brilliant physicist who went totally crazy at the end of his life. But he said, well, I have this equation that involves these values. And so what happens if I let each of the denominators here go to 0? What would happen if I let each of those go to 0? Well, they have to have certain values for x, okay, in order to let each of them each of those denominators go to 0. I'd have to have a 0. I'd have to try a 0, and then I have to try a 1/2, and then I have to try a -2. Okay, and what happens is it's a real kind of cheap and easy way to get a, b, and c if we just have linear factors, because two of the terms here, the a term, the b term, or the c term, two of those will cancel out and only be left with one left over. Let's just show how this works. If I let x be 0, okay, then what happens? I get 0 squared plus 2 times 0 minus 1 is equal to a times 2 times 0 minus 1 times 0 plus 2 plus b times 0 times 0 plus 2 plus c times 0 times 2 times 0 minus 1. And these two terms here, they go away. Okay, anything times 0 is 0. And so for each of these cases, letting x equal some nice value, it's going to clear two of those terms from me, leaving me, in this case, with just the a term. So over on the left side, I get -1. On the right side, I get 2 times 0, which is 0, times -1. So this is a times -1 times 2. So I get -1 is equal to -2a divided by -2, and a equals 1/2. Okay, so I'm left with one of my coefficients, what a is, up here in the original algebraic expression, or algebraic equation, I should say. So, okay, so let's go to the next one. Let's let x equal 1/2. Okay, so that 2x minus 1 equals 0. Okay, so now the a term and the c term are going to cancel out, because the a term and the c term are the only two terms that have 2x minus 1 is 0. 2x minus 1 in them. And if I let 2x minus 1 go 0 because x is 1/2, then I will be able to solve for the b term. And so I'm going to plug in 1/2 squared plus 2 times 1/2 minus 1 is equal to A times 2 times 1/2 minus 1 times 1/2 plus 2 plus B times 1/2 times 1/2 plus 2. Okay, plus C times 1/2 times 2 times 1/2 minus 1. Okay, and again, the A term and the C term are going to cancel out. 1/2 squared is 1/4. Okay, 2 times 1/2 is 1 minus 1, so that's going to go to 0. So this will just be 1/4. Okay, this is going to be B times 1/2, B times 1/2 times 2 plus 1/2. Well, that's just 5/2. Okay. So this is going to be 5/4 B. Okay, and I want to solve for B, so I'm going to multiply by 4/5. And so that I know now that B is equal to 1/5. So that A is 1/2, B is 1/5, and we just have to get the last one here. To get the last one, I want to let x equal -2. Okay, so that x plus 2 is equal to 0. And so we get -2 squared when we plug into the original equation. Okay, back up here, this guy here. Okay, we'll get -2 squared plus 2 times -2 minus 1 is equal to, okay, in this case, A and B are going to cancel out. But let's go A times 2 minus, or -2, sorry, -2 minus 1. Okay, times -2 plus 2 plus B times -2 times -2 plus 2 plus C times -2 times 2 times -2 minus 1. Okay, again, this is going to go to 0. This is going to go to 0. And so A and B cancel out, leaving me with just C that I could solve for. So this is going to be 4 minus 1. Those cancel. Is equal to C times -2 times, what is that? -4 minus 1 is -5.
-5.
Yeah, thank you. Okay, and so this is -1 is equal to
10C.
Yep, and so divide by 10, and we get C is equal to
-1/10.
yeah, -1/10. Thank you, Ling. Okay, so a lot of algebra, right? We haven't even gotten to the calculus yet. We're still kind of stuck in the algebra. So what did we want to do? Well, we wanted to take this guy, x squared plus 2x minus 1 over x times 2x minus 1 times x plus 2, and turn it into a over x plus b over 2x minus 1 plus c over x plus 2. And that will allow us to, that will make it easier for us to integrate. Okay. Okay, so we found out what A, B, and C are. So what was A? A was 1/2. So I can rewrite this as 1 over 2x plus, and what was B? B was 1/5. So this is going to be 1 over 5 times 2x minus 1. Okay, I'm just multiplying my expressions by my fractions. Okay, and then this is gonna be minus or plus a negative, which is minus 1/10 times x plus 2. Okay, because again, the original idea here is I want to integrate this, right? I want to take the integral of x plus 2x minus 1 over x times 2x minus 1 times x plus 2 dx, and we want to integrate this. And so now I can break this up into 3 separate integrals. And these are a lot easier to integrate with than, you know, having one big one with a bunch of factors in the denominator. So let's integrate these individually. Okay, so I'm going to pull the 1/2 out in front. And so that's 1 over x dx. And so that's just natural log. So this becomes 1/2 natural log absolute value of x. Okay, I'm not going to put a plus c until the very end. Okay, this guy here becomes 1/5 times the integral of 1 over 2x minus 1 dx. Now here I'm going to have to do a u sub. Okay, u is equal to 2x minus 1. Du is equal to 2 dx. And so d over 2 is equal to dx. So this is going to become 1/5 times the integral of 1 over u du over 2. So this just becomes 1/10. The integral of 1 over u is natural log of u, okay, which ends up being 1/10 plus 1/10 times the natural log of 2x minus 1. Okay. Okay. Okay, and the last one here, this is going to be minus 1/10 times the integral of 1 over x plus 2 dx. So this is 1/2 natural log absolute of x plus that guy. Just bring him down. Okay, and so we have, again, you could do a u sub on this, although it's a pretty easy u sub. Du is equal to dx, and so it's really just going to be the natural log of this thing. Okay, but we'll go through it. 1 over 10 integral of 1 over u du, which is negative 1/10. Negative 1/10 times the natural log of the absolute value of u. I'll put a plus c this time since it's my last integral. And so this becomes minus 1/10 times the natural log of x plus 2 plus c. Okay, now I could leave my answer that way. This would be acceptable on an exam. You could leave it like that. You could also kind of, and this is expanded form. You could put it in its condensed form if you want as well. How could we do that? So this is natural log square root of x plus natural log of 2x minus 1 to the 1/10 minus natural log of x plus 2 to the 1/10. Okay, I'm not going to get rid of the absolute value just yet. Although for it to have, because it is an even power, because in order for us to have any real solutions, these would have to be positive. because it's like the 10th root. Maybe I'll write that. So this is going to be the natural log of the 10th root of 2x minus 1 over x plus 2 uh, times radical x. So yeah, I could condense this into natural log of radical x times this thing. Yeah, we'll see. Okay. So either of those are fine. Okay, let's try another one of these. Okay, so the calculus isn't so bad. It's the algebra that is kind of a pain. Okay, they are very long problems because there is a lot of algebra. Let's jump into another one. Oh, number 2. Okay, integral x to the 4th minus 2x squared plus 4x plus 1 all over x cubed okay there we go. Okay, x cubed minus x squared minus x plus 1. Okay, dx. Now we can't immediately go to partial fractions on this, and the reason is because the power on in the numerator is larger than the power on the denominator. So x to the 4th is greater than x to the 3rd. So does anybody know what we have to do?
Long division.
Very good. Yeah, very good, Con. We must divide using long division, or it's actually called polynomial division. Okay. So many terms in math, like it is a foreign language. I think that's why people find that math to be so hard, is because not only is it a sport, but it's also a foreign language. So lots and lots of terminology. Okay, so we must divide using polynomial division. Okay, so let's do that. Let's jump into that. X cubed minus x squared minus x plus 1. Divide that into x to the 4th plus 0x cubed. I have to put a placeholder. Minus 2x squared plus 4x plus 1. And so x cubed goes into x to the 4th x times. So that's x. So now I'm going to multiply. X times x cubed is x to the 4th minus x cubed. When I said multiply x by the next term, minus x squared plus x. So now I change my sign and add, basically subtract, which is adding the opposite. So I add the opposite, 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 and opposite. So we add the opposite, cancel x cubed. This becomes negative x squared. This becomes 3x, and then bring down the 1. Okay. Nice, nice, nice. Okay, so how many times does x cubed go into x cubed? Yeah, it just goes one time, right? So 1 times this, x cubed minus x squared minus x cubed minus x squared minus x plus 1. Okay, again, change the sign and add. So subtract, add, subtract. And we get 0, 0, 0, and 4x. So this just becomes 4x. Okay, and that's my remainder. So I can rewrite this as plus 4x over x cubed minus x squared minus x plus 1. So now I've written it in a form that has, we've simplified a little bit, and it has the 4x over the, now a 4x over x cubed. So the power in the numerator, okay, is smaller than the power in the denominator, which is good. So this is my full result from long division. So this is going to help me now to do partial fractions. So this is a 3-step problem. First, we have to do long division. Then we have to do partial fractions, and then we have to integrate. So it's a jolly good time, as they would say in, you know, ye old England. Let's work on this third term here, and put that into partial fractions. Okay, we get 4x over x cubed minus x squared minus x plus 1. Okay, and so I need to factor the denominator. So I'm going to use factoring by grouping. I'm going to group the first two terms and the last two terms. And that's going to get me x squared times x minus 1 times x minus 1. Okay, good. Okay, I like what we've done there. I'm going to factor out the x minus 1. And I get x squared minus 1. And that I know factors. That's the difference of two squares into x minus 1 times x plus 1. Okay, and so I can rewrite this as x minus 1 quantity squared. X minus 1 quantity squared times x plus 1. Okay. Now, we can
Professor?
Yeah?
I have a question. Like I have been groups of like s cubed with s squared, and then I go to x squared minus 1. So the thing I have is x squared minus, no, x minus 1 and x minus 1.
Okay.
Yeah, so kind of like I get like x squared minus 1 square, but I didn't have the x plus 1.
Yeah, because I factored this guy into here and here.
Oh, okay. Thank you.
I pulled out the x minus 1 and I put it here.
Uh, where, like, I'm not really sure like where we have the x square.
Yeah, it's from the first two terms.
Oh, okay, I got
They
it.
have a common factor of x squared. So I pull out the x squared in the first two terms.
Oh,
I get
sorry.
x minus 1.
Yeah,
then
sorry, my bad. My bad.
Then I
Yeah,
pull
I
out a
didn't see
negative one. That's okay. I go fast sometimes, you know. I just,
Yeah.
you know, this is, you know, this is algebra. So, you know, sometimes I go fast through the algebra because I want to get to the calculus. But no, it's all good.
Yeah, sorry, Professor.
No, because if you had a question, then probably, you know, 7 or 8 other people did in the class too. Okay. Oops. Okay, so what I have to do here is I have to do, well, let me just show you what this is. This is 4x over x minus 1 squared times x plus 1. Okay. And the way we deal with this squared, this double factor, or what we call multiplicity, is we say that we could have had an x minus 1 in the denominator, or we could have had an x minus 1 squared in the denominator. Okay, and so we have to account for each power. If it was a cubed, I'd have to have another term that would have been a cubed. It would have been 1, 2, and then 3, all the way up to the number of multiplicity that we have. And then we have this single factor of x plus 1. Okay. Okay, so now I can clear my fractions here. I'm gonna go 4x is equal to, I can multiply both sides. Maybe I should not skip steps. Okay, x minus 1 squared times x plus 1. Okay, x minus 1 squared times x plus 1. Okay, I'm gonna clear my fractions, although when I distribute this guy to the x, only one of the x minus 1s cancels. So this is a times x minus 1 times x plus 1. Okay, because only one of the x minus 1s cancels. Then we get b times x plus 1. And then we get c times x minus 1 squared. Okay. Okay, so let's see what we can do with this. If I let x equal 1, okay, then everything goes away except for the b term. I get 4 times 1 is equal to a times 1 minus 1 times 1 plus 1 plus b times 1 plus 1 plus c times 1 minus 1 squared. This goes to 0, that goes to 0. And so I'm just left with 4 is equal to 2b or not 2b. No, it's 2b, 2b. Divide by 2 and we get b is equal to 2. Okay. Okay, the next thing I want to do is I want to cancel out that b term. So instead of letting x equal 1, I'm going to let x equal negative 1. Okay, that's good. Nice. Yep, like what we've done there. Okay, so this is going to become 4 times negative 1 is equal to a times negative 1 minus 1. It's minus negative 1 actually. It's going to go to 0. No, it's negative 1 minus 1. That's correct. Okay, and then negative 1 plus 1, that's going to go to 0. Plus b times negative 1 plus 1, that's going to go to 0. 0, 0. And so c is just going to be negative 1 minus 1. And that is squared. Okay, interesting. Okay, so we get negative 4 is equal to negative 2 squared c. Okay, and so negative 4 is equal to 4c. Divide by 4, we get negative 1 is equal to c. Okay, so c is negative 1. Nice. Okay, now all we have to do is figure out what a is. Okay, a, there really isn't anything we can do to cancel out and just get a. So, but I already know what B and C are. So I'm gonna use my algebraic superpowers. And I'm gonna say, well, I have A times x minus 1 times x plus 1. Okay, plus I do know what B is. B is 2 times x plus 1. And then plus C, which is negative 1 times x minus 1 squared. Okay. And so I could multiply this all out and compare. So this is A times x squared minus 1 plus distribute 2x plus 2 minus x squared minus 2x plus 1 equals 4x. Okay. And I'm going to write the 4x kind of weird in a second. But this all works out. I'm going to distribute the a. I get ax squared minus a plus 2x plus 2 minus x squared plus 2x minus 1. Let's see what we do with this. Yeah. So I'm going to group these terms. I'm going to write this as 0x squared plus 4x plus 0. Okay. And I'm just going to group some terms here. I'm going to say ax squared minus x squared. Okay, just rewrite this a little. And then go to the x's. This is 2x plus 2x. That's 4x. Okay, that's good. Okay, 2x plus 2x is 4x. And then plus, okay, let's group all of the constants. 2 minus 1 is 1. And so this is going to be 1 plus, or 1 minus a is the constant term. Okay. Okay, 1 minus a. So if I factor out the x squared here, I get a minus 1 times x squared plus 4x plus 1 minus a. Okay. And so what does this tell me? It tells me that a minus 1 had to be 0 because that's the coefficient of that term. What else does it tell me? It tells me that 4 had to be the coefficient of x. We already knew that. 4 and 4. And it tells me that 1 minus a has to be the coefficient of it has to be the constant term. So what number minus 1 and 1 minus what number is 0?
One.
Yeah, 1. So a had to be 1. So now we can actually do the integration. Okay. So what was it that I want to integrate? I wanted to integrate, look all the way back at our original function. This was x to the 4 minus 2x squared. Oh, let me first plug in the a, b, and c real quick. Okay, so 4x over x cubed minus x squared minus x plus 1 is equal to 1 over, the a was over the x minus 1, right? 1 over x minus 1 plus b, which was 2 over x minus 1 squared plus c over x plus 1. So this is minus 1 over x plus 1. Okay, so that's that guy. However, we did have, at the beginning, we had an x plus 1 plus this thing, right? Okay, so don't forget that we're not just integrating the fraction part, we actually had, okay, another part to it. So we have x plus 1 plus 4x over x cubed minus x squared minus x plus 1 is equal to x plus 1 plus 1 over x minus 1 plus 2 over x minus 1 squared minus 1 over x plus 1. And we want to integrate this. Integrate. Integrate. So I actually end up doing 5 different integrals. Nice. I can integrate each of these terms separately. So the integral of x, that's x squared over 2. The integral of 1 is just x. Those are the easy ones. The integral of 1 over x minus 1 is natural log of x minus 1. Okay. The integral of 1 over x minus 1 squared, okay, that's a u sub. So u is equal to x minus 1, du is equal to dx, right? So this is really going to be the integral of 2 over u squared du. Come on. Scroll. There we go. Okay, 2 over, so this is 2u to the negative 2 integrate, which is add 1 to this. So this is negative 1, divide by negative 1, negative 2u to the negative first. Okay, which is negative 2 over u. But what was u? It was x minus 1. So this is negative 2 over x minus 1. Okay, that's the next term. And then we have this minus 1 over x plus 1. Well, that's just, I could do a u sub on that. It's just very simple. It becomes du is dx, but it's just 1 over natural log. Or it's just 1 times natural log of x plus 1. Okay, plus c. Oops. Something is not happy. Okay. Can I scroll now? Yeah, okay, good. Okay, plus c. Okay. And so my final result is 1/2 x squared plus x plus natural log x minus 1 minus 2 over x minus 1 minus natural log absolute value of x plus 1 plus c. Now I could combine the natural logs if I wanted to into one term. And I could get 1/2 x squared plus x minus 2 over x minus 1 plus natural log of x minus 1 over x plus 1 plus c. Always plus c. Okay. And that's it. Wasn't that fun? Yep. Okay, let's talk about a special integral real quick. The integral of 1 over x squared plus a squared dx is equal to 1 over a times the inverse tangent of x over a plus c, okay? And the way we do this is through a u substitution. The derivative of tangent, inverse tangent of x, okay? If I take the derivative of, let's just do x over a real quick. Okay, what I get is I get 1 over what is it? What I get? Yeah, I get 1 over x over a squared plus 1. Right, if I take the derivative of that. And so, but then I have to take the derivative of the inside, x over a, so that becomes times 1 over a. So that's chain rule, right? Okay. Okay. Yeah. And so, actually, let's do it the other way around. Let's put the 1 over a inside. Okay, if we get the derivative of this is going to be 1 over a, right, times the inverse tangent times the derivative of x over a should just be it should be 1 over a. Yeah. Times 1 over a. Okay, I think this will work out. And that equals 1 over a squared. Okay, yeah, times 1 over x squared over a squared plus 1. And so what I'm going to do is I'm going to distribute this a squared. Okay, I'm just showing that you can go forwards and backwards. That this is actually correct. This is true. This becomes 1 over x squared. Oops. 1 over x squared plus a squared. Okay, if I take the derivative of that, I get, if I take the derivative of the answer here, I should get what's inside the integral, and I do. Okay, so it checks. Check. We could also do it backwards using a u sub. It's okay, but I would have to divide by a squared first. But you get the idea. This works. This is good, and this should be something like this should be on your formula sheet. Okay, it might say u instead of a, I don't know. Different formula sheets use different variables. But this is going to help us in our next problem. Okay. Okay, number 3. Oops. We have the integral of 2x squared minus x plus 4 over x cubed plus 4x. Okay. Okay, dx. Okay, so I'm gonna factor the denominator. The power on top is smaller than the power on bottom, so I don't have to worry about long division. And so we have 2x squared minus x plus 4 over x times x squared plus 4. Now that's not factorable, that x squared plus 4. It's not factorable. So how do we deal with this? Well, we can still break this up. It's x, a over x, because again, a is, it's x is a linear factor, so I can put a. However, x squared plus 4, it's not linear, it's quadratic. And so we always have to go one degree less complicated, or 1 power less in our denominator. We have to account that, basically a constant is 1 degree less than a linear, and a linear is 1 degree less than a quadratic. So I have to go x squared plus 4, and then I have to say, well, this could have been bx plus c. The linear component also has a constant. Okay, so I'm gonna just put a little side note here that says, hey, the numerator is always 1 less degree in complexity than the denominator. Okay, so the numerator is always 1 less degree in complexity than the denominator. Again, we have to account for the fact that, if it's a linear factor, then what's one degree less complex? A constant. If it's quadratic, what's 1 degree less complex? It's linear. What if I had, something that was x cubed plus 5, right? Or 5x squared plus 3x plus 1, and this was not factorable. Then I would have to have ax squared plus bx plus c. Okay, I'd have to account for the fact that the numerator could have been a quadratic, and all of its splendor, and all of those terms. Okay, because I don't know what quadratic it is. The quadratic doesn't necessarily go through the origin, just like I don't know what linear expression I'm going to have if I have a quadratic in the denominator. Okay, so it's always 1 less degree in complexity. Okay, so we've seen what happens when we have multiple roots. You just have to account for every case, and we see what happens when we have higher powers in the denominator. We have to account for we have to go 1 less degree and account for every coefficient. Okay, so now we can actually do some algebra and get this into a state where we can integrate. Hey, that rhymed. Okay, so if I multiply through and clear my fractions, I get 2x squared minus x plus 4 is equal to a times x squared plus 4 plus bx plus c times x. Okay, so I just multiplied both sides of the equation by x and x squared plus 4. Okay. Okay, so in this case, I can't do the Heaviside technique because it's going to fail me. I don't have linear factors. I can only do the Heaviside technique of letting x be something fun, trying to solve for another variable. So what I'm going to do is I'm going to expand this. I'm going to multiply this out, and I'm going to try to compare term by term. So this is ax squared plus 4a plus bx squared plus cx, okay, after I distribute. So, okay, this is going to be helpful. Okay, let me just get this into a form that allows me to compare a little. Okay, so we have 2x squared minus x plus 4 is equal to, I'm gonna group the a x squared and the bx squared to be a plus b x squared. And then I'm gonna put the cx there and I'm gonna put the 4a there. Okay. So what does this tell me? This tells me that a plus b had to be 2. This tells me that c has to be -1 and that a had to be 4, no, 1. And a had to be 1. Okay, because the 4 a's has to be 4. We won't skip that step. Maybe I will. Okay. So 4 is equal to 4a, so a is equal to 1. So if a is 1 and a plus b is 2, then b is 1. Okay, so 1 plus b is 2, so then b is 1. Okay, cool. So what? So let's plug these back in to up here. Okay, for A, B, and C. And let's see what we can do. Okay, so we have A is, what was A? A was 1. So this just becomes 1 over x. Equals 1 over x. And then B was 1. So that just becomes x. And C is -1. So that's just -1 all over x squared plus 4. But through the power of fractions, we can break this up into a common denominator. This is 1 over x plus x over x squared plus 4. Okay, minus 1 over x squared plus 4. Cool, 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 cool. Okay, and we're going to actually integrate these 3 different ways. Because again, what's the point of this? It's integrating them. Okay, and the integral of this thing was the integral of the original 2x squared minus x plus 4 over x cubed plus 4x. That's what this thing became. Dx. Okay. So let's just take this term by term and integrate. If I integrate 1 over x, that's just natural log of x. If I integrate x over x squared plus 4, well, that's just a u sub. U is equal to x squared plus 4. Du is equal to 2x dx divided by 2. And we get the integral of x dx is on the, so that x dx goes with, that x goes with my du over 2. And so it's just 1 over u du over 2, which is going to integrate to 1/2 natural log of u. Okay. But what was u? U was x squared plus 4. Okay, so u, so this is 1/2 natural log of x squared plus 4. Okay, so that's the second term. I have my first term, a second term. Let's do the third term here. This is minus, now I'm gonna use that uh that formula that we talked about and said, well, this is 1/2 inverse tangent of x/2 plus c. And where'd I get that from? Well, I gave you the formula right before this problem. Okay, so let's put this all together. This is the natural log of absolute value of x plus 1/2 natural log of x squared plus 4 minus 1/2 times the inverse tangent of x/2 plus c. Okay, and you could leave that answer like that if you wanted to. I might clean it up a little bit more. Let's see what we can do. This could be natural log of x, absolute value of x. Yep, okay. Absolute value of x times the square root of x squared plus 4. Okay. I wouldn't need the absolute values there. I could get rid of the absolute value when I square root it, because it has to be positive anyway. Okay, and then minus 1/2 inverse tangent of x/2 plus c. Okay, so either way, that's fine. Either way is a suitable answer. Okay, and that's 7.4. Let's continue on with 7.5.
Why is the second term, how did it become a square root?
Because the 1/2, right? Powers of natural log,
Okay.
right? And then anything to the 1/2 is a square root. Maybe I'll put it like this. Natural log of that guy. 7.5 says basically everything that we've learned up to this point. This is 7.1 through 7.4. Okay, basically says, how do we strategize when we're given anything, any type of integral? What's our strategy here? So this is strategies. Okay. Okay, 7.1 through 7.4 combined is what 7.5 is. And it's again strategies for integration. Okay, so basically we see an integral problem. How are we going to approach it? How are we going to tackle these really complicated integration problems? Okay, and we have some helps. Okay, some helps for you. Okay, strategies for integration. Number one, simplify. Okay, simplify the integrand if possible. Okay. Number two, look for an obvious substitution. Okay, number three, classify the integrand by its form. Ooh, what are the forms? One, we could have a trigonometric integran. So that might just lend itself to utilizing properties of trigonometry or trig substitution. Is it trigonometric? Is it a rational function? Okay, are we gonna have to use natural logs? Are we gonna have to use long division? Or what are we gonna have to do? Is it products of functions? Which lends it to integration by parts. Okay, are there radicals involved? Like the square root of x. I should put plus or minus here. It's gonna get rid of the whole thing, but that's okay. I need to buy a new eraser. Ah. There we go. Okay. Sometimes my eraser works, sometimes it doesn't. Square root of plus or minus x squared plus or minus a squared. Okay, does it involve radicals? Then that would lend itself to, sometimes it would lend itself to integration by parts. Okay. Oh, not integration by parts. It would trig sub. Sorry, trig. Okay, number 4. Okay, try a different approach. Okay, like, you know, praying. No, I'm just kidding. Okay, so try a different approach. Okay, maybe take a break and come back and try something different. Can't spell different. Different approach. Okay. Different substitution. Okay, different order for parts. Okay, some useful integrals, and this should be on your formula sheet. Oh. Okay, so some useful intervals that we can use inside other problems. Okay, the integral of secant squared x is tangent x. The integral of secant x tangent x is secant x. Okay, the integral of secant x is natural log of secant x plus tangent x. The integral of tangent x is the natural log of secant x. The integral of cosecant squared x is negative cotangent x. The integral for cosecant cotangent is equal to negative cosecant x. Yeah, I'm leaving off the dx's and the plus c's, but you know, you get the idea. The integral of cosecant x is equal to the natural log of cosecant x minus cotangent x, natural log of cosecant x minus cotangent x. Okay, the integral of cotangent x is equal to the natural log of sine x. Okay, the integral of gotta wait. You good? No? Yeah, exactly. Always plus. Okay. And so, the integral of 1 over x squared plus a squared dx. What was this? This was 1 over a inverse tangent of x over a plus c. Okay. The finally, oh, now I go too far. Okay. The integral of 1 over x squared minus a squared is 1 over 2a times the natural, oh, there's a dx, times the natural log of x minus a over x plus a plus c. Okay, and the integral of 1 over the square root of a squared minus x squared dx, that's just the inverse sine of x over a. Come. Okay, so we get x over a plus c. And the integral of 1 over x squared minus a squared square root is dx is equal to the natural log of x plus the square root of x squared minus a squared. Okay, and the plus, if I have a plus here, this just becomes plus. What I can really do is I can do plus or minus, and then plus or minus. It just means that if it's positive, it's the answer is positive. If it's negative, the answer is negative. And instead of writing two formulas, we just write kind of 2 and 1. Okay. Okay. Okay, let's do a few problems here. Okay. Number 1. Take the integral of tangent cubed x over cosine cubed x dx. Okay, so this is going to be the integral of tangent cubed x times secant cubed x dx. Okay. And so when we have some odd values, okay, of tangents and secants. Okay, we can break off a tangent secant to get everything in terms of secants. The goal is to get everything in terms of secants. So I want to break off tan squared x secant squared x, okay, times tangent x secant x dx. And so now we want to change everything to secants. So tangent squared is going to be secant squared x minus 1 times secant squared x times tangent x secant x dx. And the reason we want to change everything to secants is because the derivative of secant is secant tangent. Okay, so this becomes secant to the 4th x minus secant squared x times tangent x secant x dx. And so now we can just do a u sub. Come on, Mr. Mouse. Give me some love. There we go. Okay. Now we're going to say, well, this u is equal to secant x, du is equal to secant x tangent x dx. So this is my du right there. So this is going to be the integral of u to the 4th minus u squared du, which is 1/5 u to the 5th minus 1/3 u to the 3rd plus c. But what was c? C was what was u? U was secant x, so this is secant to the 5th x minus 1/3 secant cubed x plus. Okay. That was number 1. Problem number 1. Okay, so that was using trig functions. Okay, let's do another one. The integral of e to the radical x dx. That's interesting. E to the radical x dx. Okay, so we're gonna do a u sub on this. U is equal to radical x. However, when we do our du, this goes kind of wacky. This is 1/2 radical x dx. And so this, if I multiply both sides by 2 radical x, this becomes 2 radical x du equals dx. But what was radical x? Hold on. 2u du. Radical x was u. So that becomes dx. So this becomes, okay, the integral of e to the u times 2u du. Okay, so this becomes the integral of 2u e to the u du. Very nice. And so now we do integration by parts, right? Okay, so using Liate, the exponent is the last, so I don't want that one. I'm going to use the algebraic, okay, which is first. So I'm going to let u equal 2u. It's kind of weird to let u equal 2u, but that's okay. We'll just go with it. Okay, and then du is equal to 2 du. Again, kind of weird to let those be the same, but we could use a third variable if we really wanted to. And so v is equal to e to the u, because dv was equal to e to the u du. So we integrate here, differentiate here. Okay, and so I'm gonna go uv minus v du. So this is 2, give me that pen back. Still my pen. 2u e to the u minus the integral of 2e to the u du. Nice, 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 nice. Okay, so now we've got 2u e to the u minus the integral of this is just 2e to the u plus c. But what was u? U was radical x. So I could actually factor out a 2 and an e to the u. And then I get u minus 1 plus c. And then I'm going to plug in radical x. And I get 2e to the radical x times radical x minus 1 plus c. Practice, practice, practice. And more practice. Okay, number 4, or no, sorry, number 3. Okay. Number 3 is the integral of 1 over x times the square root of natural log of x, okay, dx. So this one lends itself nicely to a u sub, because if I take the u is equal to the natural log of x, then du equals 1 over x dx. So here's my 1 over x, and there's my dx. So this just becomes the integral of 1 over the square root of u du. That's nice. So this becomes u to the negative 1/2 du, integrate. If I add 1/2 to that, or if I add 1 to this, then that becomes u to the 1/2 divide by 1/2, right, plus c. Well, dividing by 1/2 is the same as multiplying by 2. So this is 2u to the 1/2 plus c. But what was u? U was natural log. So this becomes 2 natural log of x to the 1 plus c. I could rewrite that in terms of square root, because again, we leave our toys the way we found them. If the question has in it a square root that of natural log, and I have a square root of natural log in my answer, then I leave it the way I found it. We always leave things the way we found them. Okay, don't make your elders angry. Okay. Okay. Okay, let's try another one that's a little spicier. Let's spice it up. Let's throw some Tabasco or some Tapatio on this. Just spice it up. Okay, the integral of the square root of 1 minus x over 1 plus x dx. Okay. So interesting. Yes, I like what I've done here. I haven't done anything. So let's see where we can go from here. let's take the square root of 1 minus x over the square root of 1 plus x dx. I'd like to get an x squared in the denominator because that would allow me to do, I don't know, trig substitutions or, you know, just some nice stuff. If I got an x squared in the denominator, that would make me happy. So what can I do? Well, I can multiply by the square root of the conjugate here. So we're gonna conjugate these. So square root of 1 minus x, square root of 1 plus x, square root of 1 minus x. There's my magic 1. Okay, I didn't change anything. I just multiplied by 1. But what does this allow me to do? This allows me to do the square root of 1 minus x quantity squared all over the square root of 1 minus x squared, difference of two squareds. Squareds? Difference of two squares, I should say. Okay. So that cancels. So that's just 1 minus x over the square root of 1 minus x squared. Oh, okay. So now I can put this over a common denominator, break this up into two separate integrals. 1 over the square root of 1 minus x. Oops. 1 minus x squared. Come on, give me my squaredy squared. I gotta stop making mistakes. It's way too time consuming. Maybe that should be on a t-shirt. Stop making mistakes. They are way too time consuming. Okay, minus the integral of x over the square root of 1 minus x squared. And these are each dx. Okay, why do I break it up? Because I have to use two completely different strategies for each of these. This guy will integrate nicely to inverse sine. This is the inverse sine of x. Okay, why? Because the derivative of inverse sine is exactly what is in the integral. That is the definition of the derivative of inverse sine. Okay. The other one here, we're going to do a what?
U sub.
Yeah, U sub. Thank you, Mai. Okay, we don't do trig sub because we could, although it's overkill, right? It's overkill to do trig sub here. So we're just going to do U sub. So U is equal to 1 minus x squared. Du is equal to negative 2x dx divided by negative 2. Okay. And we get the integral of 1 over the square root of u times negative du over 2. Nice, nice, nice. Okay, I'll pull the negative 1/2 outside. Negative 1/2 times the integral of u to the negative 1/2. Okay, du, and a negative and a negative. Okay, make a positive. So this is inverse sine x plus 1/2. Okay, times the integral of this guy. But what is the integral of that guy? Don't I just add 1 to this? Let's just add 1, right? And that gives me 1/2. And so we just divide by 1/2, which is the same as multiplied by 2. Okay, and so this becomes u to the 1/2 Divide by 1/2. Oh, look, the 1/2s cancel. That's nice. Plus C. Don't forget the plus C. Always plus C. Okay, and but what was U? U was 1 minus x squared. Whoops. Come back. Come back here. You scrolled too far. Oh my gosh. Stop with the lag. Stop with the lag. Okay, so sine lag is for chumps. I said no chumps. Okay, so U was 1 minus x squared to the 1/2 plus C, but we're not going to leave it like that. Inverse sine of x plus the square root of 1 minus x squared plus C. And what was that equal to? That was equal to the integral of the square root of 1 minus x over 1 plus x to dx. Wow, that was a lot, right? That was a lot. We covered a lot today, but it's good stuff. Well, let me stop my recording. Okay.